regression. So this is part one of a two-series session. So we'll be discussing simple linear regression in today's session, and we'll be working majorly with or solely with SPSS today. Have you guys had any class before now on linear regression? I think an R class has been done on linear regression. Is that correct? Yep, good. So let us get into it. I'll share my screen and then I'll just advise that we launch our SPSS right away, because that is where we'll be working from entirely today. We'll be working with the resident doctors data set, which I believe all of us or most of us should be familiar with. And we'll be using that in today's session. Right. So I will share I wouldn't call them slides per se. It was a presentation that was prepared by another colleague of mine, but I'm just using it to teach today's class essentially. And we will be referring to that presentation, now and again. So I'll just share my screen so that you guys can see. If I'm going too fast, please feel free to stop me at any point. Right. So we are discussing the simple linear regression majorly today. And as we might probably know, the simple linear regression is sort of a statistical model that we normally use to make predictions. We want to know, if A is, if you can use, A to predict variable B, the go-to statistical model to use for that is the simple linear regression. And to make this class as practical as possible, we will just dive right into it so that we ask our questions and talk through things whilst we are, doing the practicals. So I want us to launch our SPSS and import the resident doctors data set. I have mine imported here already. For those who can't remember how to import, can you all see my SPSS screen? Just tell me if you can't. Okay, so I'll assume everyone can see my screen. Good. So to import your resident doctors data set, you just click on File, Import Data. Because it's an Excel data, you click on Excel, and then you click on Resident Doctors, and you click Open. So mine has been imported already, so I won't go through the process again. Or, alternatively, I can actually. Let me close my SPSS and redo it from the start, so that we are all on the same page and working at the same pace. Right. So I think the admin has generously posted, sorry for the infinity screen. The admin has generously posted the screen to the data set so that you can just go on the link to the data set rather. So you can just go on there and download what you need to download. So importing the data set, click on File, Import Data, click on Excel, and then I have mine here, and then I click on Open. And then OK. And yes, so that's my data set imported. So on the Excel, on the SPSS sheet, you will see, at the bottom, you will see two different tabs. There's the data view, where you have the entirety of the data set. And you also have the variable view, where you just see the variables only. And we will be making reference to this data view and the variable view today as we take this class. So going back to our presentation, now the pertinent questions that we want to ask today with a simple linear regression model is, we want to find out, is there a way that we can predict the mental health score of these resident doctors based on the number of hours worked? I mean, looking at it ordinarily in a setting like Nigeria, or typically the medical setting, you may want to just assume, hypothetically speaking, you may think that, oh, the more people work, the worse of their mental health score may be. So we want to test that hypothesis. We want to see if somebody works more, does that make any changes? Does that affect their mental health score in any way? And that is the question that we want to ask with this simple linear regression model. Now, when you are doing a simple linear regression, you need to have your predicting or independence variable, okay? So the predictor or the independent variable in this case will be the hours worked, because we want to know if hours worked could affect mental health score. And in this case, the dependent variable, or otherwise called the outcome variable, is going to be the mental health score. So doing this on SPSS is quite easy, but there are some caveats, and we'll go through them, when we are doing our simple linear regression. So I want us to open our SPSS, and to do the simple linear regression is quite straightforward. You click on Analyze, you come down here to Regression, you click on Linear, and then it shows you this very nice page. So you have your section for the dependent variable and another section for the independent variable. Our independent variable or predicting variable is hours worked. So we'll click on it, we'll click on this arrow, and then it pops up here. And then the dependent or outcome variable is the mental health score. So you click on it, you click on this arrow, and then it pops up there. Now, you go ahead and click on Statistics, and you check a few boxes here. So one of the boxes that I want you to check is this one that says Durbin-Watson, and I would explain as we go along why I've told you to check that box. So you click on Durbin-Watson. Sorry, let me just turn off these notifications. Right. So you click on Durbin-Watson. Click on confidence intervals as well, to get a bit more data, a bit more information. You click on Continue. And then you come to Plots. Here, you click on Plots. Now, this is ZPRED. ZPRED is Z predictor. Because we are trying to do a simple linear regression model, we want to have an x-axis and a y-axis, and I'll explain all of these things as we go along as well. So ZPRED, because that's your predictor variable or independent variable, that would always go on the x-axis. And ZRECID is the residual variable, and that will go on the y-axis. You check histogram, you check normal probability plots, you click Continue, and you click OK, and you let SPSS do its thing. So SPSS has come back to us with a lot of information, lots of tables, lots of information, and we need to try and make sense of all of this jargon that we can see on the screen here. So we'll start from the top and we'll gradually work our way downwards. Now, when you're doing a simple linear regression on SPSS, some of the most important things, the important parts of the table, are your model summary. That's the model summary table. A table we call the ANOVA table. ANOVA is analysis of variance. And you'd also have your coefficients table. Those are the three most important ones. And you have these extra tables that are not, and these charts that are not as important as the other tables that I mentioned earlier on. Now, before we get into the explanation of this, I want us to create a scatter plot. So a scatter plot is like a form of graph, it's like a chart. And to do that on SPSS, let me just go back to the meeting for a second. Let's be sure that there are no questions or I'm going too fast. Are we all on the same page? Can you guys give me a thumbs up so that I'm sure I'm not just speaking to myself? Okay, right. That's reassuring. Thank you. Okay, so I want us to create a scatter plot before we go into the explanation of tables that Excel has generated for us. Because I think it's better we do that ahead so that we can, have a proper explanation of the whole thing once and for all. So to create a scatter plot, you click on graphs, you click on chart builder. Okay. And then you see on this section, you see scatter/dot. And then you click on it. And then you choose this scatter plot, this first one here, you double click it. And this chart comes up, this one here. So again, like before, we put our explanatory or independent variable or predictor variable, hours worked. We drag it to the x-axis. And then we'll take the mental health score, we'll drag it to the y-axis. On this linear fit lines section here, you check this box saying total. And you click OK. And you let SPSS do its thing. And it comes up with this chart. Now, the reason I wanted us to go through this first is because when you want to do a linear regression, before you can say, okay, I want to do a linear regression to check this, there are some assumptions that must be met before a linear regression is the appropriate statistical model for you to use. If those assumptions are not met, then a linear regression perhaps may not be the most appropriate thing for you to use for your data analysis. Now, one of the assumptions is there has to be a linear relationship between your independent variable and your dependent variable. And you can tell by looking at this chart. Now, looking at this scatter plot, the dots the variables seem a bit all over the place. They seem everywhere. But SPSS is telling us that, yeah, there is some level of linearity. It doesn't particularly look linear, looking at it on the ordinary. And if you take a look at this line here, you'd see that it's a negative line. So the positive lines are usually this way. If there's a positive correlation, you see the lines will go like this. And if there's a negative correlation, you see the lines will run like this. So the first assumption is there has to be a linear relationship between both variables. So if you do a scatter plot, and what you are seeing instead of a straight line is you are seeing a curved line or a line that is, shaped like a moon, then that is not linear. So there's no linear relationship between both variables. So in that case, your linear regression may not be the most ideal model for you to use. Now, that is one assumption. There are still many other assumptions, and we'll go through all of them. The other assumption is that the variables must be independent of each other. So it means if an observation has been recorded under, maybe the hours worked, for instance, ideally, the next observation that will be recorded for hours worked should not be dependent on previous observations. It should be independent of them. It means, it's fairly representative of what you get if you just draw a random sample from the population. And we will see the test for this assumption also on SPSS as we go along. The other assumption is for you to use a linear regression model. A linear regression model is ideal when you don't have outliers in your data set. Because if you have outliers in your data set, that may affect your regression output and it may affect the kind of results that you get. And again, when we are going through the results, you would see how to check for outliers in your data set as well. The other thing is, I believe they must have told you about the concept of residuals in linear regression. Is that something that you guys have heard of, residuals in linear regression? Just give me a thumbs up if you have. Good. Good. Right. So for your residuals, one of the other assumptions is for you to use a linear regression model, your residuals must have a normal distribution. It must be normally distributed. And you can check this in two ways. Through a histogram and putting the distribution line, I'm putting a normal distribution curve over it. And you can see that this is normally distributed here. Or alternatively, using something we call a PP plot. So this is a PP plot of the residuals. And what you are checking in this case is how close these dots are to this central line running across. If the dots are close to the central line, like this one, then yes, the residuals are normally distributed. But if the dots are all over the place, the dots are far apart, then no, the residuals are not normally distributed in that case. I will still recap all of these things again so that we do not forget, so that we understand. And then the last, one of the other assumptions is something we call homoscedasticity. It's just, so this one you test for by basically just looking at this chart here, this plot, this one that I'm highlighting here. And what you're looking for is this. If you see that this dots, all these variables here, if you see that it forms a very nice pattern, like a cone-shaped pattern this way, a cone-shaped pattern, then, or alternatively, a less than sign, less than is this way. So if you see it forming, the dots are sort of aggregating, coming together to form a nice cone-shaped pattern, or it's forming like that less than sign, then your regression, model may not be the ideal one to use. But if the variables are scattered all over the shop this way with no clear pattern, then yes, you can use your linear regression. Now, we already generated our output from SPSS, and we want to try and make sense of the results that we have. So starting from the top, the first table, as I mentioned, is the model summary table. You have something here we call the R. What this R means is just your correlation coefficient. So what R is saying is how related, what is the strength of the correlation between, the dependent variable and the independent variable. And as you guys will probably know, R, the values will normally vary from -1 to +1. -1 means there's a strong negative correlation. The sign in front, minus or plus, is the direction, and the number is the magnitude. So this number here is the magnitude. Oftentimes, SPSS may not give you a negative or positive sign in front, regardless of what the direction is. What you just see is SPSS will give you the magnitude, and you may need to check the direction yourself with your scatter plot, one of the ones that we looked at earlier on. So the R here is your correlation coefficient. In this case, there is a sort of weak correlation between the hours worked and the mental health score, because this is just 0.2. So, I mean, it's not 0, so it doesn't mean that there is nothing. At the same time, it's not particularly strong. It's just 0.2. So yes, there is some correlation, but it is weak. The other thing we want to look at again is R square. R square, can anyone tell us what R square means? Just so that the class is a bit interactive. Can anyone tell us the meaning of R square? If you've discussed it in previous sessions, maybe under the R session, does anyone know the meaning of R square from SPSS? Any takers? Okay, so the meaning of R square is how much of the changes what percentage of the changes in your dependent variable can be explained by your independent variable? What extent, what degree of changes, what's the percentage of changes of your dependent variable that can be explained by your independent variable? And we would normally convert this figure here to percentage. So 0.042 is approximately 4.2%, which is weak. So 4.2% is quite small. So that means only 4.2% of the changes in mental health score can be explained by changes in hours worked. So I will take that again. Only about 4.2% of the variability, the changes in mental health score, which is our dependent variable, are attributable to the predictor variable, changes in hours worked. An adjusted R square is just basically adjusting this R square that you have here for the sample size. So it's not particularly extremely useful. The second table that we come to is your ANOVA table. And in this ANOVA table, what you are looking out for is this SIG section, your significance level. Now, for most of the analysis that we will do, we usually set significance level at 0.05%, and then we'll say, anything less than 0.05% is statistically significant. Anything that is more than 0.05% is likely, not statistically significant. So we have 0.09%, 0.09 here. So that is less than our significance level of 0.05. So, and that is, statistically significant. So this ANOVA table is basically telling us that, okay, how good is this independent variable? How good of a predictor is it? How good is this regression model that we have put together? And this significance level is telling us that, okay, perhaps it might be a decent, predictor, it might be a decent model. But don't forget that before you can even get to the stage where you are generating these tables and doing your linear regression at all, the assumptions that we discussed earlier on must have been fulfilled. Now, another table, perhaps one of the most important tables, is the coefficient table. That's the third table. Are we familiar with the equation for linear regression? Are we familiar with the equation for linear regression? Good. So does Humphrey want to help us with what the equation of linear regression is?
Yes. Usually it's derived from the line equation, that is y is cos mx plus c. So in this case, y is the outcome. The outcome variable, and which is equal to bo, which is usually the intercept.
Okay.
The y-intercept, and then plus b1, depending on how many independent variables you have. For simple linear regression, we have one independent variable.
Yep.
So we expect that will be the slope of the equation.
Good. So that's absolutely correct. Thank you very much. So this is a very important table, as I was saying earlier on. And the bits that you want to pick from this table are this constant here. So this one that says constant, that is actually your intercept. And what this simply means, what this number simply means is when x is at 0, that is when hours worked, your independent variable is at 0. This is the value of y. So 26.352 approximately is going to be the mental health score when hours worked is 0. Now, what does this other one at the bottom mean? This is your slope. And the simple meaning of this is for every unit increase in hours worked, what changes will you observe with the dependent variable, the mental health score? And this we can interpret to mean for every increase in hours worked by 1 hour, your mental health score reduces by 0.037. So that is what we've been able to glean from this table. And we can actually use this table in the equation, like Humphrey generously explained to us, to make deductions, okay? So we can always, tweak things around, tweak the number of hours worked, and we'll see, how the mental health score changes, based on that equation. Now, coming down here, this table is just an extra table. It's not part of the standard, linear regression outputs that you get. But I want us to go through it because it is one of the tests that we do to check for some of those assumptions that I mentioned earlier. Now, this residual statistics, you recall that I mentioned about the presence of outliers. And I said if you have outliers in your data set, there is a chance that the regression, the linear regression model may not be the most appropriate one for you to use. And how do we check for the presence of outliers using SPSS? By doing this residual statistics. And the part that you look at this last row that says STD, that's standard dot residual. You look at these two columns, minimum and maximum. So these two numbers are the numbers that we are interested in. And they would generally say and assume that if the minimum, if this number ranges between -3 to +3, then it means you don't have outliers. In this case, we can see this one is -2, which is still within that range, but this one is slightly above 3. So this is indicating to us that there is a possibility that our data set may have some outliers. So it's worth noting that as well. And I think we've been through all of these other tables. So let's go back to our slide. And it's worth noting that in the real world, when you collect actual data, there is a chance that your data set may not fulfill all of these assumptions. There is that possibility, and you should just be aware of it. I think we have not particularly touched on the Durbin statistic, Durbin-Watson rather. Where is that answer again? Just bear with me. Okay, there we go. So that's our Durbin-Watson number. So again, this Durbin-Watson, I forgot to touch on it when we were discussing about this table. This Durbin-Watson statistic that you can see here is just to check for the independence. I mentioned earlier on that one of the assumptions, that must be fulfilled before you can use a linear regression model is the variables, the observations should be independent of each other. So when you draw a random sample in the population, it should be fairly representative. And this Durbin-Watson helps us to test for that assumption. Now, also, they would generally say that values of 1.5 to 2.5 for this Durbin-Watson, would indicate that, yes, the observations are independent. But in this case, we are getting numbers of about 0.415. So this is telling us that there is a chance, it's very possible that the observations that we have drawn, for our hours worked mental health score, there is a chance that they are probably not independent of each other. And if you draw a random sample in the population, the samples that you get may not be, the sample that we have gotten in this data set may not be representative of what we get, what we've gotten in the normal population. Now, putting all of these assumptions together and all the jargon that we've been discussing all day, do you guys think that a linear regression model is ideal to explore this relationship, this prediction that we are interested in? for the trying to determine, if the number of hours worked could be a good predictor of mental health score. Do you think the linear regression model will be ideal to do that, to explore that relationship? Yes or no? You can just type in the chat box if you don't want to unmute yourself. Anybody? Okay. So I don't think so, because we have a couple of assumptions that have not been fulfilled. So linear regression model might not be, the ideal thing to use in this case, but that's a discussion for another day. So going back to our slide, we have been able to touch on how to interpret the findings. We have been able to do a simple linear regression with discontinuous variables. Does anybody have any questions on that before we move on to the next part of this linear regression?
Sorry, I have a question.
Yes, please.
Please, can you please go through how the scatter plots? Yeah, because I don't know, I kind of missed how you were able to select the variables.
Okay.
And run it on the outputs. If you can go through that again. Thank you.
Not a problem. So for your scatter plot, you click on graphs in SPSS at the top. You click on chart builder. Okay. So you click on scatter plots. You see scatter. When you see choose from section here, you see lots of options here. You click scatter. So to bring out all these options for you. And then you just click on scatter plot. You can double click on it. You drag your mental health score. Click on it and drag it to the y-axis, which is because that's your dependent variable. Dependent variables always go on the y-axis. And then the independent variables will always go on the x-axis. So hours worked is our independent variable. So you just drag that to the x-axis as well. And then as soon as you are done doing that, you just click OK. And once you click OK, Excel generates a scatter plot for you, exploring the relationship between the two of them. If you are interested in the scatter plot for the residuals, the histogram for the residuals and all those other bits that we got from our results, you do that through here. So you click on Analyze, Regression, Linear. You check in your dependent variable, mental health score. You put in your independent variable, hours worked. And for some cases, you can simply end it there and click OK to get your, your ANOVA table, your model summary table, and your coefficient table. But if you want a bit more, and when I say a bit more, if you want to test some of those assumptions that I mentioned earlier on, then you need to check a few extra boxes. So that is when you come to statistics. You click on the Dubbin-Watson to check for independence of your observations. You check your confidence intervals. If that's something you're interested in, you click on continue. You come to plots. Now, this is for your residuals majorly. You check in your Z-pred, that's predictor. I mentioned earlier on that predictors or independent variables always go on the x-axis. You check it into the x-axis. And then I also said that the residual variable, the other one, Z-resid, goes on the y-axis. You check on histogram, check on normal probability plot, so that it gives you both the histogram showing you whether your residual statistic is normally distributed or not. Remember that I said for you to do, for your linear regression model to be used, for it to be ideal in this situation, your residuals, need to have a normal distribution. And that is essentially what you're just trying to check by checking those boxes here. And then you click continue, you click OK, and you let SPSS do its thing, and it generates results for you. Does that explain it better? Were you able to follow? Good. So let us do something different. We will do a simple linear regression with binary predictors. our first one that we did our simple linear regression with continuous, predictors. It was continuous data. But this time around, we want to do it with binary predictors. So binary predictors just means you have two independent variables, basically taking the values of either 0 or the value of 1. And I'll show us how to do that on SPSS. It's not, it's not difficult either. Now, this is what you have to do. We would first need to create, because we are trying again, what we are still trying to do is we are trying to explore the relationship between mental health score and hours worked. But we are trying to see whether, okay, if we divide hours worked, if we just split hours worked into two categories, into binary date, into a binary variable, does it give us a bit more information? Does it explain a couple of things to us? What do we get from it? Splitting it into a binary predictor, into binary variable, does it tell us?
Sorry to interrupt.
Sorry?
Sorry to interrupt. I just wanted to ask a question.
Yes, please.
So when we are dealing with binary predictors, how is it different with from logistic regression?
So logistic regression, with your logistic regression, most times you are dealing with binary outcomes. So more of yes or no type questions, binary outcomes majorly. But in this case, it's the binary predictors that we are keen on, not the binary outcomes. We are still looking at the outcomes in general, still trying to make some predictions, but we are using only binary predictors this time around. Whereas with logistic regression, oftentimes is the outcome that is often binary rather than just the predictors alone. In this case, our outcome has not changed. We are still trying to explore the continuous outcomes, but we are using binary predictors instead. In some cases, you can also do a simple linear regression with categorical predictors. So rather than using just two, sections, the binary predictors, you can decide to split it into different categories. And we'll also touch on that briefly as well today in this class. I think as part of this course, I think there are sessions on logistic regression, if I remember correctly. And I think they would explore it and go into it deeper at that point in time. So for us to do a simple linear regression with binary predictors, we need to convert our independent variable to binary variables. As I said before, the independent variable is also called the predictor. So to convert it to a binary predictor, what we do is this. We click here, we click on transform on SPSS, and we click on recode into different variables. So what are we trying to recode? We are trying to recode the hours worked. We are trying to split it into two different sections. So if you click on hours worked, you check this arrow, it moves into this section. And then you change the name because we are creating a binary variable. So we don't want it to affect, we don't want to permanently alter this hours worked data set, this hours worked variable. That's why we are creating a new set of variable. So we can call this hours GT70. And you click change. So you have changed hours worked to hours GT70. You can decide to put in a label. So hours worked above 70 hours. And then you click on change. And then you click on old and new values. So what do we do with this old and new values? We are trying to, as I said, we are trying to split the data sets into two different, just binary variables. So let us pick those who have worked 0 to 70 hours. Let's use 70 as our midpoint. So those who have worked 0 to 70 hours, and then those who have worked above 70 hours. So range, you click on this one that says range, value through highest. And when you click on range, value through highest, you put 70 in here. And then you come to value, you assign the value 1 and click on add. or rather we can put 0 and click on add. And then we click on all other values. We come to value here again. We put 1. We click add. We click continue. And then we click OK. So if you go ahead and look on your data, on your variable view, you will see that it should have automatically added hours GT70 to it, which you can see there. And if you look on your data view, if you scroll to the side, you would see that the ones that have worked, oh, I think we did it the other way around. So what we want is I'll show you why I said we did it the other way around. So if you look at 80 hours worked here, you will see that it has been assigned the value 0. 50 hours worked has been assigned the value 1. So what has happened here is everyone who has worked more than 70 hours has been assigned the value 0, and everyone who has worked less than 70 hours has been assigned the value 1. But I wanted us to do it the other way around instead. So this was an error, but we can easily just correct that. So let me go back to transform, recode into different variables, hours worked GT, old and new values. So I just change this to 1. And then I change this to 0. Oh, no. So that's 0. That's 1. So I think that should have solved the problem. Good. So that is what I wanted. So now you see that we have managed to change it back. So for everyone who has worked more than 70 hours, 70 hours and above, they are assigned the number 1. And for everyone who has worked less than 70 hours, they are assigned the number 0. And we can use this in our simple, regression. So if you come to linear, rather than using hours worked in this case, we uncheck hours worked, and then we use hours worked above 70 instead as our independent variable. I'm not very keen on all these other tests at this point, so I'll just uncheck some of those boxes to give us a simple output. And then we click OK and wait for Excel to do its thing, SPSS to do its thing. So we end up with this result. Now, interpreting this result, again, this is the 0.97 is the coefficient, is the correlation coefficient. 0.009 is our R square. So we are trying to see how much of the dependent variable, how much of the variability in our dependent variable, how much of the variability in mental health score can be explained by hours worked, our binary variable, specifically hours worked above 70 hours and hours worked under 70 hours. And we also have our ANOVA here, our ANOVA table. We can see that the significance level here is 0.220, which tells us that, yeah, there's a very high chance that there is no stats. I mean, you can probably not use this as a reasonable predictor. You cannot use hours worked above or under 70 hours as a reasonable predictor of the mental health score. The linear regression model might not be a good fit because this number here is far higher than our significance level of 0.05, sorry. And if you come to our coefficient here, our coefficient table, we have our intercept, that is 24 hours. That's 24, sorry. And then we also have the slope here, which is minus 686. So interpreting this, now some schools have taught to interpret this to mean when the hours worked is zero, less than 70, this is the average, this sort of the mental health score that you get, 24. Now, when the hours worked for each increase in the units, so in this case, we are moving from category, because we're dealing with binary variables, so we are moving from category 0 to category 1. So for an increase, moving from category 0, that's less than 70 hours worked, to category 1, more than 70 hours worked, we can, there is a chance that the mental health score will reduce by 0.686. Again, this is not an appropriate regression model, and we can see it here already from our ANOVA table with this, very high significance value, which is way above 0.005. But this is just for explanatory and illustrative purposes, just for us to see, how some schools of thought would use a regression model with binary predictors. But again, it's obviously not ideal in this situation. And I'll just do a recap again. We were looking at using simple linear regression with binary predictors. And we started by creating a new binary variable, hours GT70. And we did that by clicking on, we opened our SPSS, we clicked on transform, we clicked on recode into different variables. What we were interested in recoding was hours worked. So we clicked on hours worked. We changed the name in this area here to hours GT70. We assigned it a label saying it means hours worked above 70 hours. And then we came here, we clicked on old and new values. And then when we clicked on old and new values, we clicked on range, value through highest. We put in 70 there because we are splitting it into two ways with 70 as the midpoint. And when we typed in 70 here, under new value, we assigned it the number 1, meaning anything from 70 and above gets assigned the number 1. And then after doing that, we clicked add, and we came back here, we clicked on all other values. After clicking on all other values, we assigned it the number 0. So, because essentially all other values in this case would just be values that are less than 70. And then after we assigned it the value 0, we clicked add, we clicked continue, we clicked change here, and then we clicked OK, and we let SPSS do its thing. And when SPSS did its thing, we checked the output under our data table. So you would see that for people who have worked more than or equal to 70 hours, they get assigned the number 1. And those who have worked less than 70 hours get assigned 0. The last bit that we will touch before we take questions and do a recap of some of the assumptions again is simple linear regression with categorical variable. So simple linear regression with categorical variables to test for linear trends. Now, this is very similar to simple linear regression with binary variable, but in this case, we are working with multiple categories of the predictor variables rather than just, 2 categories. 2 categories means it's just binary. But in this case, we are working with multiple categories. So we want to see, what it looks like when we split up the predictor variables into different categories. And how do we do that? We go back to our SPSS. We click on transform. and we'll click on recode into different variables. Let's uncheck this one because that's not what we are interested in at this time, but we are interested in hours worked. So we'll put our hours worked in that box. And let us assign a name of hours cat to this one. And then let's say the label is categories of hours worked. You click change it here to hours cat. And then we'll click on old and new values so that we can assign the numbers. Now, from category 0 to 40, because let us start with 0 to 40, 0 hours worked to 40 hours. We click on range, lowest through value. We punch in 40. And assign this the value 1. Let me remove this ones first. So range, lowest true value. We put 40 there. We assign this the value 1. We add. For our subsequent categories, you then click on this range here instead. And then you say 40.001 to 60. You assign that the value 2. And then you come back to range again, 60.001 to 80. We assign that the value 3. We add it. And then we want values that are sort of 80 and above. So we come here, we say value through highest, values that are 80 and above, we assign them the value 4. We click add, we click continue, and we click OK. And we check our Excel, our data view page to see what has happened. So you will see that SPSS has created a new variable category for us called hours cat. And what SPSS has done is this: for everyone who has worked 0 to 40 hours, it's assigned them the number 1, just like we told it to do. For everyone who has worked 40 to 60 hours, it's assigned them the number 2, just like we also told it to do. For everyone who has worked 60 to 80 hours, it assigns them the number 3, like we wanted it to do. And for everyone who has worked more than 80 hours, so 89, 90, and the likes, it assigns them the number 4, like we wanted it to do. Are we all on the same page for now? Is anyone having any difficulties getting to this point? Oh, Humphrey raised their hand. Humphrey, please speak.
Oh, I had asked the question, sorry. I had asked the question already.
Okay,
Sorry.
okay, all right.
It's as if you are muted, sir.
Oh, sorry, I was muted.
Yeah.
So I said if you look on the data view, you would see that the hours category 70, hours cat variable has been created in a separate column. And under the variable view as well, you'll see that we have hours cat as a different variable, just like we wanted SPSS to do. Now, what we want to do now is we want to do our regression analysis again. So regression, linear. So rather than hours worked above 70, we put our hours cat there, categories of hours worked above 70. I'm not sure why it's not coming up with hours cat here and why it's coming up with the label instead, but it doesn't really matter. Right. So we click on statistics. We have our estimates checked. We have our model fit checked. Continue. Not particularly interested in any plots this time. We click on OK. And then we wait for the SPSS output. So we are looking at this results. Again, similar interpretation to the previous ones. This is the correlation coefficient. This is the magnitude of the correlation. How much, how related is mental health score to number of hours worked? And similarly to the other results we got before, 0.2, which is some correlation, but not very strong. R square, this again is how much of the dependent variable, how much of the variability, the changes in the variance, the changes in the dependent variable can be explained by changes in the independent variable. Still small, 0.042, that's approximately 4.2. And then we then look at our ANOVA table. So it has a significance value of 0.009, which is saying that, okay, perhaps the use of this categorical, predictors may make this linear regression a decent model after all in predicting the values of our dependence variable. That's the mental health score. Coming to our coefficient here, our coefficient table, the constant is 25.82. The constant is just basically the intercept. So what is the mental health score when, one has not worked, when the x is equal to 0? So this is the y-intercept. Categories of hours worked, that is our slope. And the slope, again, like we mentioned earlier, is what is the unit change in your dependent variable, or in this case, our mental health score, with a unit increase in number of hours worked, our independent variable. And in this case, it is minus 0.731. So ideally, just like somebody pointed out the other time, simple linear regression is most ideal, best for continuous variables. Very useful, illustrates things properly for you. There are some times where when you are calculating, let me see how best to put it. When you are trying to do simple linear regression, and when you have when you want to use your line equation to make predictions, as part of the line equation, you have a part of the line equation that is your y-intercept, which is when x is equal to 0. And that is usually the constant. But you need to know that in some cases, when you are looking at some type of data set, it's not possible for your x to be 0. Your x cannot be 0. It just cannot happen. It's not possible. I'll give you an example. If somebody has done, let's say, you did an exam in medical school. Now, for those who went to medical school, you probably know that Nigeria uses a closed marking system where you can't score 0. So it's not possible for you to get 0. You maybe can get a minimum of, let's say, 12, and then you can get a maximum of perhaps 80%. Now, imagine that you want to use a simple linear regression model, but in this case, you want to use the score from medical school exams to determine the person's mental health score. So in this case, your predictor variable, your independent variable, is the medical school exam results, and then your outcome variable is the mental health score. But we know that it's not possible for you to get 0 in the medical school exam. So in that case, your line equation may not be appropriate for you to use, because we know that you just cannot get 0. So you cannot have that value. So it's worth always noting that and being aware of it. I think I will just do a quick recap on the assumptions of the linear regression that have to be fulfilled again. And then we'll take questions for those who might be struggling with one or two things in SPSS. We can, just go through it, and we will call it an evening. So some of the assumptions that have to be fulfilled, as I said earlier, your variables, your observations must be independent of each other. Okay, so the observations must be independent of each other, and you check that with this Dobbin-Watson, this result that we have here, this output. They would normally say that if it ranges between 1.5 to 2.5, then the observations are independent of each other. That's one. We also want the independent and predictor variables to have a linear relationship. And you can check that with the aid of your scatter plot with regression line just across it. It gives you an idea of whether or not there is a linear relationship. If you have a curved line, along the scatter plot, then it's probably no linear relationship between both variables. The other one is your residuals. You want to be sure that your residual variables have a normal distribution. And you can do that by charting them in an histogram or a histogram and putting a normal distribution curve over it to see how it looks like. Or alternatively, you can do a PP plot and watch the approximate distance from this residuals from this line of best fit here, this line that runs across. That's another thing you need to be aware of. And the last one was to check the homostaticity. So again, this is something that you just look at. It's sort of like an eye test, really. You see how well, or you see if this variables here, this point here, fit into a pattern. If it forms a nice cone-shaped pattern or like a bracket type pattern, then that is hetero, not homo. And if there is no clear pattern to it, if the variables are just all over the place like they are here, the observations are everywhere, then that is good. And then your linear regression model may be ideal. I'm not entirely sure what the tutor in linear regression model 2 will be teaching, but I believe they will probably expand on some of the concepts, the basic concepts that we've touched on today. And they might probably introduce, a bit more concepts to you on that simple linear regression. Does anyone have any questions, any struggles, anything that you're not clear about, working with SPSS at all?
Sorry, excuse me.
Yes, please, go ahead.
Yes, please. I'm kind of struggling with that same scatter plots because when I tried from my end here to get the scatter plots based on how you walked us through it, I noticed that I wasn't able to. The scatter plot is not coming up. Yeah, so I don't know if it's from my end. So I don't know if you could just walk me through that.
So do you want to share your screen?
Yes, please.
Okay, share your screen so that we can have a look at it as a class, and then we can walk through it.
I don't know if I'm permitted to share. If you can just
yes, please share your screen.
So share.
Stop sharing mine. Okay. Whilst you're trying to do that, can we take Humphrey's question?
Yes, thank you so much. I just wanted to understand when we divided the hours worked into different categories, and we got our beta coefficients. So how is it different from the earlier where we just had the hours worked and the outcome variable, and also did we expect an output where we have different categories being displayed, for example 40 hours and the beta coefficient?
So I think we started with working with only continuous variables, isn't it? And then we looked at the results of the results that we got for the continuous variable, and then we are able to estimate, how the mental health score changes with each change in the unit of the the predictor variable. When we did the categorical one, now the way people would look at it, the difference in both of them would be with the categorical data. You are looking at, okay, if somebody crosses, maybe, we split into, we did 0 to 40, we did 40 to 60, we did 60 to 80, and then we did above 80. So what you're looking at in that case is if somebody crosses from one part of the, if somebody jumps from one category to another, so let's say you move from working 30 hours to working 50 hours. So you have crossed from one category to another category. The question you are trying to then ask at that point is, how does the dependent variable change when you cross the hours worked category? And that is what we are looking at by splitting it into categorical data. As I said, this might not be the most ideal data set to do that, but just for illustrative purposes, we're able to see that, okay, if somebody crosses from 30 hours to 50 hours, for instance, the mental health score could reduce by this number of units. Or if somebody is working the baseline number of hours, the mental health score is estimated to be this number. So that's just the purpose of it, really. It's just seeing, how things change when we try to tweak and play around with the predictor variable, how that might change the dependent variable and the kind of equation that we come up with, basically. Has Greg been able to share his screen? Okay, Greg, can you open your SPSS so that we can have a look?
I'm trying to share. I don't know why I'm not able to share the exact SPSS page.
So you probably might need to share your entire screen. And then you have to then go and sort of manually click on the SPSS page, if that makes it easier.
Yeah. So I should stop sharing. I don't know why I'm not able to share this. Just trying to see if I can just share this quickly. So share my entire screen. Share this. I don't know why I'm not able to share it. Okay, I think I've seen it.
Okay.
Yeah, I've shared this now, yeah. Okay, that's it. I don't know if you can see.
Let me see. Yes. So what are you trying to achieve?
Yeah, the scatter plots. Yeah, so
if you click on graphs,
yes, okay.
chart builder.
Chart builder. Yeah, so this is what is popping up. That is not really showing me where to put the X and Y axis.
Oh.
Yes, so I don't know
And
why
there is no sort of another pop-up window or minimized window somewhere that is not showing.
No, so this actually got stuck. So I wanted to, if this had actually come up to show me the X, I would have just put that and just plot the.
Are you using a trial version of SPSS?
No.
Yeah, you're using the full version.
Yeah, the full version. Yeah.
Oh, that's slightly confusing. I'm sorry, I don't know why that is happening.
I don't know why it's not.
I'm not entirely clear why that is happening. Sorry. I can't tell you this is exactly why it's happening.
Okay. So I don't know. So just try to do this, but I don't know why it's not coming up there. So it should have just come up with the.
Yeah.
I don't know why it's coming up this way.
I'm not entirely sure why that is happening, to be honest.
Okay. I'll just keep troubleshooting. I don't know. All right. It's okay. Thank you.
No, wow.
Yeah.
Is anyone else confused about any of the things that we've done today? I mean, I reckon when you watch the video over again and then you go and play with some of the data, the other variables in the resident doctor's data set, there is a very high chance that you'll be able to, get a better grasp of the concept and also find some of the things that you can even do more with SPSS. Yeah. Do we have any other questions? No? All right then. So we shall call it an evening. Thanks very much for joining this session today. And yeah, speak to you soon.